In this experiment, we will be performing a weight-bearing test to investigate the ability of a 3D printed prosthetic to lift the same objects that a human hand could. We want to answer the question, is an Arduino 3D printed prosthetic hand able to bear weight like a human hand? This is an important question to ask and test because prosthetics are necessary for many people living without limbs, a number that stands at about 2 million in the United States alone today. It is necessary to ensure that people have functioning prosthetics that can work like a natural hand. Electrically powered prosthetics usually work by picking up the electric signals generated by the existing muscles of the patient. These are usually picked up by EMG sensors, and those signals are interpreted as movements for the electric hand to carry out. In our experiment, we will be using flex sensors to facilitate this instead. We hypothesized that overall, an Arduino-powered 3D printed prosthetic will not be able to bear as much weight as a human hand.
Here are the materials for this project. We 3D printed each component of the hand. We brought those together using fishing wire as well as hot glue gun. For the circuitry component, we used an Arduino Uno, 3 servo motors, as well as some resistors with jumper wires. Additionally, we used styrofoam and cardboard to stabilize these two diagrams together, as well as using aluminum foil, carbon paper, and cardboard to create our flex sensors. Here is the overview of our design. We programmed the code in the Arduino builder. The laptop connection then sends that code and programs the Arduino Uno and sends the instructions. This Arduino Uno then powers the first breadboard in which the glove is connected. These right here are the flex sensors. When you put your hand in and move the glove, the flex sensors indicate a motion movement. This sends the message to the breadboard, sends it to the Arduino, and the Arduino communicates it to the second breadboard, which is powered by the 9-volt battery. And this signal is then sent to the servo motors, causing the fishing wire, as you can see that are attached right here, to move the string and causes the fingers to then contract. Here's the overview of our circuit. On the left side, we have the mini breadboard, which is powered by the 9-volt battery. The 3 ends over here on the servo motors indicate a ground, a signal, which goes to the Arduino Uno, and a positive, which is the power supply. On the right side, we have our 2 flex sensors. These are getting powered by the Arduino Uno, and the output is being sent to the Arduino Uno. We have 2 resistors over here, which are 22K ohm resistors. However, on our design, we did not have a second 22K ohm resistor. Therefore, we put a 10K, 10K, and 2K in series for an equivalent of 22K resistors. So at this point, you're probably wondering, how in the world did we even make these flex sensors? Well, it was very simple. We used cardboard, aluminum, carbon paper in the middle, aluminum again with cardboard. To hold all of these together, we used hot glue on the sides, as can be seen. In order to send the signal from this to the breadboard and Arduino, we needed to connect an exposed metal wire to the aluminum layer. This exposed metal wire could then be used to connect and hook the jumper wires to the breadboard pins. In this experiment, we tested 3 hypotheses. In the first bullet point, we hypothesized that if a 3D printed hand is tested for force strength, then it will slightly underperform on average compared to a regular functioning human hand. In the next 2 bullet points, we directly target the 3D printed thumb and 3D printed ring finger, in which we stated that the thumb of the 3D printed finger will actually be stronger than the 3D printed ring finger, but both will be weaker than the human fingers. Here we have the experimental setup, with different weights ranging from 1 grams as a 3D printed part to 94 grams with the chubby marker. We attached these weights to the finger using a bit of super glue so that when the finger contracted, the weight would not fall off to the side. In our design process, we had the control as the human hand and the experimental as the robotic hand, in which both attempted to lift the weighted items. We had 10 trials per item, which are these 10 items, as listed on the previous slide. We then determined whether the hand would be able to lift the item, not be able to lift the item, or partially be able to lift the item. This data was then graphed on Excel. Here's a short clip of the hand lifting a bolt.
2, 1. These graphs were generated from the data we were able to collect during the experiment. Whether or not the finger was able to lift the object and to what extent were quantified as seen in the table on the right. The x-axis depicts trials 1 through 10. The y-axis depicts to what extent the object was lifted, and the lines correspond to the object. They are all seen in the legend above the data. If the finger was completely able to lift the object, this was quantified by assigning a number 2. If the finger was only partially able to lift the object, this was quantified by being designated the number 1. 0 was designated when the finger was unable to lift the object at all. As seen in the graphs, the human ring finger was completely able to lift no more than 70 grams. The human ring finger was only partially able to lift the 86-gram washer for the first 7 trials before being unable to lift it at all. The human ring finger was completely unable to lift the 96-gram chubby marker. The ability of the human ring finger to lift objects was relatively consistent. The same cannot be said regarding the 3D printed ring finger. Like the human ring finger, it is in fact able to lift the first 9 objects consistently. However, it is sporadic in its ability to lift the 86-gram washer and the 94-gram chubby marker. The human thumb was completely able to lift no more than 70 grams. The human thumb was only partially able to lift the 86-gram washer for the first 3 trials before being unable to lift it at all. The human thumb was completely unable to lift the 94-gram chubby marker. Again, the ability of the human thumb to lift objects was relatively consistent. Like the human thumb, the 3D printed thumb was able to lift the first 9 objects consistently. However, it is again sporadic in its ability to lift the 86-gram washer, and it is completely unable to lift the 94-gram chubby marker. Our results help us analyze the hypotheses we proposed earlier. We are unable to assert whether the 3D printed prosthetic fingers are stronger or weaker than the human fingers when it comes to lifting the objects, given that the ability of the 3D printed fingers to lift objects was sporadic. In accordance to our original hypothesis, the data suggests that the 3D printed thumb is not able to fully lift more than 70 grams, although it is partially able to lift the 86-gram washer. Contrary to our hypothesis, the human thumb is unable to lift up to 90 grams. It is only able to fully lift up to 70 grams. Contrary to our hypothesis, the 3D printed ring finger is able to lift up to more than 40 grams. Also contrary to our original hypothesis, the human ring finger is unable to fully lift more than 70 grams. The 2 most important things to take away from this experiment is that prosthetics need to be as strong and as reliable as natural hands. They need to be able to consistently lift as much weight as a natural human hand, while also being able to be lightweight so that they are not difficult to yield. Our experiment showed that the prosthetics were less reliable when it comes to lifting objects. Given the results of our experiment, we can conclude the following. The sporadic nature of the 3D printed finger's ability to lift objects made it difficult to determine which finger is stronger, the human finger or the 3D printed finger. The 3D printed ring finger is stronger than the 3D printed thumb. The human fingers are more consistent than the 3D printed fingers, which are variable. These conclusions are important for us to understand what is needed for prosthetics in the future. We need to ensure that prosthetics are as strong and consistent as natural limbs. During the development of the 3D printed prosthetic, we experienced issues with the printing that impacted the way these parts came out and may be responsible for the ability of this prosthetic to lift items. The servo motor may have also affected the ability of our device to lift an object. For example, we needed to use 2 servo motors to move the thumb of the prosthetic, as one was not strong enough. In the future, we would need to fix this component to keep it consistent and make sure it is strong enough. We can consider a wider array of objects to test to get a more comprehensive view of what the fingers are able to lift. Additionally, we could improve our data collection method. We should spread out the trials to avoid muscle fatigue as a negative factor in our results. Another way to improve our experiment is by better quantifying the finger's ability to lift objects. For example, by considering the angle of contraction.